All right, we're going to sketch y equals x squared minus 9 over x plus 3. First thing we're going to do is look at the non-permissible values. Non-permissible values are some of the most important things when you're trying to sketch a rational function. So in this one, non-permissible values always come from the denominator, and it's what makes it equal 0. So in this case, the non-permissible value is negative 3, so x cannot equal negative 3 is my restriction on this graph. That's also the domain, actually, for this function. So it's just whatever makes the denominator equal 0. And now I'm just going to simplify this rational function, and then we're going to sketch it on Desmos and see what happens. So x squared minus 9 is a difference of squares, so I'm going to factor it. So it factors as x plus 3, x minus 3. X plus 3's will cancel out because they're both binomial factors and they're exactly the same. And so we're left with y equals x minus 3. So we need to see what does that non-permissible value do. So when we graph this, we don't graph it from the simplified version. You always graph it from the original. So this simplified form, I know exactly what y equals x minus 3 is from Math 10. This is a linear function, and it's written in the y equals mx plus b form, right? So I know it's a linear function with a slope of 1 because there's a 1 attached to x that isn't written, and the y-intercept is negative 3. All right, so let's graph this on Desmos, but always remember, graph the original. The original is the one that has all the information we're looking for. So I'm graphing y equals x squared minus 9 over x plus 3. And when I look at it, there is a line with a slope of 1. So it's going up 1 over 1, up 1 over 1, up 1 over 1. And its y-intercept is negative 3. And I can just tap that point, and there it is, 0, negative 3. So what was I talking about? It sure does look like y equals x minus 3. I don't see any differences here. So what I'm going to do is we're going to actually change it from y. I want to change it to f of x. And the reason I want to change it to f of x is then in Desmos I can actually substitute different x values in. And there's one in particular. I want to find out what's happening at that non-permissible value. So I'm going to put in f of negative 3. And what it says is that it's undefined, which makes sense because you can't divide by 0. So then what's happening is when I look at this graph, I look at where x is negative 3, and I don't see anything. There's nothing there. And it's because it's just in this one instant. There's no point. There's points everywhere to the right of negative 3, and there's points everywhere to the left of negative 3. But at negative 3, there's nothing there where this non-permissible value is. So non-permissible values always stay as non-permissible values. And what it creates here is what's called a hole. Basically, for any rational function, a non-permissible value is always what is called a discontinuity. What our job is we got to figure out what type of discontinuity it is. So this one, where the x plus 3 cancels out, so their non-permissible value basically goes away when we simplify, it always creates a hole. So if we graph the function y equals x minus 3, well, the graph looks exactly the same, but at negative 3, there's a y value, negative 6. So that negative 3, negative 6, well, it doesn't exist on y equals x squared minus 9 over x plus 3. So that's why it's called a hole. Everything else is exactly the same, but there's this one spot where there's nothing there. So when we graph this, we actually exaggerate it. So if I go, oh, negative 3, negative 6, and I want to sketch this graph, well, I actually put a circle there, so it's like a hole in our graph. So this is really exaggerated because the reality is it's just an instant in time, and my circle's bigger than just at one point, right? But we exaggerate it, and we kind of make this big circle, and that's our hole. And then I got my function. I'm just going up 1 over 1, up 1 over 1 to get the other points, and I can graph it to the right and graph it to the left. So this hole is what is called a discontinuity. And the idea of it being a discontinuity is that you can't draw this without lifting your pen from the paper. So something is continuous if you can draw it all with one line, but here you should actually be lifting your pen, going over the hole, putting it down, and then continuing on. Let's see if we can find some other properties of this. So this is the hole. Now let's look at the y-intercepts and x-intercepts. So the y-intercept on this graph is at -3, and where it actually comes from is if you go the constant of the numerator over the constant of the denominator, you get the y-intercept is -3. Why that works is because a y-intercept, you always make x equals 0, so you just ignore the x's. So -9/3 is -3. And now let's switch and start looking at the x-intercept. So I just kind of marked it in green, and the x-intercept there is +3. So where does it come from? Well, if we look at our numerator, x-intercepts always come from the numerator. It's anything that'll make the numerator equal 0 that doesn't get canceled out is an x-intercept. So if it gets canceled out, well then it's a non-permissible value and it's a whole. If it doesn't get canceled out, it's an x-intercept. Domain's easy. We already got it with the non-permissible values, but it's just that you can write it in two different ways. So you can write it as the technical way, which is x is a real number such that x cannot equal -3, or what I will accept is you can just write the domain is x cannot equal -3. So it's implying it can be everything else. Okay, just summarizing, the important ideas here are, first, you can always find your y-intercept by dividing the constant in the numerator by the constant in the denominator. Second, you can always find wholes by any non-permissible value that whatever factor it is that makes the non-permissible value, if it cancels, so in this case it's x plus 3, creates a whole at -3. And lastly, an x-intercept is whatever makes the numerator equal 0. So we've dealt with one type of discontinuity. Now we're going to do another example to see a different type of discontinuity.